My name is Muhammad Al-Shadiq.
My name is Randy Harsarizal.
My name is Rizky Sakti Pradipta.
My name is Michael Abraham Listiawan.
My name is Faris Pusponegoro.
My name is Ain Nadira binti Buhari. I will talk about our final project, which is Pelton turbine, one of the engine machine. Engine machine is fluid machine that work by converting fluid energy into mechanical energy. It's applied in many industries, especially in power plant industry. As a mechanical engineer, knowledge about working principle and engineering design of the engine machine is really necessary. The turbine is pure impulse turbine which converts hydraulic energy to kinetic energy before entering runner or the turbine wheel. The conversion of energy occurs in the nozzle, which in high potential energy of water is converted into kinetic energy. The water coming out from the nozzle will hit the series of buckets, passing around the turbine wheel and the center of the jet, tangent to the inner circle of the buckets. The angular speed of the turbine wheel is affected by the amount, speed, and the diameter of the jet. Basically, the turbine is connected to horizontal shaft and electric generator. Due to the constant rotation speed of generator, the tangential speed of wheel must also be constant despite the change in loads. The effective flow entering the buckets can be formulated by rho g cube head.
Material selection. Why is material selection important? Material selection is important to fulfill a design requirement for a certain application. The application for this case is the Pelton wheel. Pelton wheel requires the material to be waterproof. Materials for this case also has to be cost efficient. For a material to be cost efficient for a particular application, it needs to be cheap and also easily formed into a shape of our wanting. Why is this important? Why will this lower the cost of production? Because if the material requires processes that involve power machinery, that will also increase the price.
Continuing on from the material selection, so for the Pelton wheel we have two parts, as you can see here, which are basically the runner and the blade. So the material chosen are, first, for the blade we chose plastic as it is water resistant, which meets the requirement. We can also form it to the shape which we wanted, so we have no problems of cutting it without power tools. We can do it in our own rooms, and because it's so cheap, we don't have to worry about breaking it. So for the runner we chose a material called Definicel. Why we chose the material? It's basically, first, it has good strength. It can hold the blades in place while the Pelton wheel operates. It is also easy to deform, so we can cut the slits in which we put the blade in it. We can shape it into whatever circle we want. And lastly, because it's cheap. Better than cheap, it's actually a second-hand material which we got for free. So that is it.
It is essential for any engineer to have a calculation before designing and even manufacturing it. So there are two factors, which is the blade, the number of the blades, or in the equation you can see that we denote it as Z, while the beta angle, when the fluid hits the blade and separates, it is the beta angle, as you can see in the experiment module 2. Now, for the number of the blades with the Z, it has two factors that considering it. Which is the capital D and the lowercase d. The capital D actually is the diameter of the Pelton turbine, the wheel, and so on. And it is the overall of the Pelton turbine, while the lowercase d is the diameter of the jet. While for the second one, the second equation, as you can see here, we calculated by using a PowerPoint while taking a picture of the spoon itself. I will show you now how the beta angle is developed in the Pelton turbine. So, in this calculation, or in how we depict it, we're using what we call common tools, which is the PowerPoint. the PowerPoint, we utilize the photograph of the spoon itself. As you can see here, the splitter that we attach in the spoon is actually the hypotenuse, and it has a fixed distance, while the spoon itself has developed some kind of skewing angle that should be fixed in terms of direction, while it is not fixed in terms of distance. While now we try to make what we call as a 90-degree triangle. Well, and then after that we can get the better angle, or the half of the better angle. We multiply it by 2, and then we get the better angle. So then it concludes both of our calculation needed for designing and manufacturing and testing and so on.
So, moving on from material selection and design, we'll talk about efficiency. We can get the equation for efficiency is power output divided by power input. So,
now I would like to continue the discussion of what Alshaz have said before. And for the calculation for the efficiency is power output divided by the power input, and for the power output itself is voltage multiplied by the ampere, and for the power input is rho, or the density of the water, multiplied by the Q, or the flow rate, multiplied by the G, gravity, and H of head. Now, as we can see from this graph, the calculation is multiplying all of the factors here, and then we get the final value of the efficiency, and for the total efficiency is 0.024%. It is relatively low because it is not as we expected as before. This is probably because the amount of the head delivered from the fluid system itself is already high, which is 14.23 psi, and the debit of the water is already high also, about 9 liters per minute. So as a result, compared to the output, there is 0.9 in voltages and only 4 milliamps for the current. It will produce the low amount of efficiency. Now, let us discuss about the cost-wise of that efficiency.
so was this all worth it? It was definitely worth it for cost-wise. The cost-wise was relatively low, and for experience, this has been a wonderful experience. We would like to give thanks to Mr. Budi Arso and his assistant for their time. Thank you.